Last meaningful lecture of the semester. Today we're going to talk about the Big Bang. So we can all sing together. The whole universe has been a million years ago. Okay. Let me preface the lecture by reminding you that yes, I am a creationist. I do believe that in the beginning God created the heavens and the earth. Furthermore, I believe that in 6 days He created life on this earth. I match my beliefs, my theological beliefs, with the scientific beliefs in that I believe that when the Bible says, in the beginning the earth was void and without form, that's not saying that when Christ created life on this earth in the literal, I believe, 6 days creation, that was the beginning of the earth and the beginning of the universe. Right? Because if the earth was void and without form, it means it was here. And so I take that to say that the creation of the universe is a different time than the creation of the earth. And what's the time? Don't care theologically. Since I don't know and don't care theologically, then I feel very comfortable taking our best interpretation of science for when the universe began and how the universe began. Now, let's go one step further here before I get into it. How did the Big Bang begin? I've told you Fred Hoyle, the person who came up with the term Big Bang, did not believe in the Big Bang Theory. He came up with the term kind of in a mocking way, saying, what do these people believe created the universe? It just, boom, there was a Big Bang, and out of nothing we had something? Fred Hoyle did not believe that there was a God, and he believed that it's impossible to have something come from nothing, much like the song goes. The Sound of Music. Nothing comes from nothing, nothing ever could. And so he rejected the idea because he thought that it required there to be a God. Now, I pretty much agree with Fred Hoyle. I believe that there is a God, and I believe that God is what created the laws of physics, which is basically what we've been studying in this class. In astronomy, we're studying how the laws of physics govern our universe, and then He put in the energy. So I just want to make it really clear that I'm not up here teaching you, evolution and all this stuff. I believe firmly that God created all. Okay, so let's get started. Unless anyone wants to have a nice theological debate on this before we do. No? Okay. How old is the universe? So we talked before about Hubble's constant, and Hubble noticing that everything is moving away from us. The farther away, the faster it is. Doing a linear fit, it had a pretty good fit. Now, the textbook points out that over the last 50 years, the value of that Hubble constant has come much more precise. We believe we know it much better. We still don't know it well, though. It's still kind of fuzzy. But if the universe is expanding and the rate of expansion has always been constant, so there's an assumption. If the rate of expansion has always been constant, then we can simply take the rate of expansion and extrapolate backwards and should be able to find the age. Take the size of the universe, the rate of expansion. But using Hubble's law said that the speed of expansion is Hubble's constant times the distance, right? If you look at any object, the speed at which it's moving away is Hubble's constant times the distance away. And so since time is distance over speed, we just replace speed with Hubble's constant times distance, and look, the distances cancel. And so the age of the universe should just be 1 over Hubble's constant. So rounding Hubble's constant off to a rough number because it's not well known, the textbook says, we're starting with this number, and then later on, we're going to change it to another number just because it fits better with the age. We're going to go with this number. It's 70 kilometers per second per megaparsec. And so kilometers per second per megaparsec, just by using the rules for dividing fractions, That's 1 megaparsec over 70 kilometers per second. Well, megaparsec is just a unit of distance. So I replace 1 megaparsec with 3.086 times 10 to the 19th kilometers. And now my kilometers will cancel. I'm left with 1 over 1 over seconds. Of course, 1 over 1 over seconds is just seconds. So we have the age of the universe is 4.41 times 10 to the 17th seconds. Or in years, that's 14 billion years. So that Hubble constant gives us an age for the universe of roughly 14 billion years. There's a plus or minus there of about 5%. So what's 5% of 14? Well, 5 times 14 is 7. So it'd be, between 13.3 and 14.7, roughly speaking. What was the assumption I said when I started this?
It's constantly expanding at a constant rate.
Assuming that we have constant expansion for all time. Well, it's probably not the best assumption. Here are different options we could have, depending on the density, that is the mass per unit volume in the universe. If there's a lot of mass, what's going to happen? Just think in general terms, not worrying about Big Bang or anything. Just in general terms, if there's a lot of mass, what happens? I heard slower, what did you say?
I feel like the more the mass takes a lot slower.
Okay, it would expand slower. That's getting a little more clear now, I understand. The more gravity you have, the more you have pulling in, right? So it shouldn't expand as quickly. The less gravity you have, the more it expands. So density, the more dense something is, the less it should be expanding, the more likely it is to contract. So if the density is too high, you start with a Big Bang, but you have so much density that it stops the expansion and pulls it back in and crunches. And so they call that the big crunch if the density is too high. So if you look at this picture is showing the Big Bang is when each line leaves the horizontal axis. So depending on what the case is, this could be the Big Bang, or this could be the Big Bang, or this could be the Big Bang, or this could be the Big Bang. And if the mass is really large, well, the density, you have that. You have a big crunch right here. How long does it take for that? Well, in this picture, it would be about roughly 14 billion years from Big Bang to Big Crunch. Now, that's just for one density. But it corresponds to that's roughly what we just calculated for the age of the universe. Well, obviously, that can't be exactly what's going on. What happens if the density is above a critical value? We're going to have a universe that grows and then shrinks and comes together. You don't have a long-lived universe. On the other hand, if the density is really, really small, then everything will continue to expand forever at a reasonably constant rate. And that's the calculation we did. We did the calculation for basically zero density. What's the outcome if the universe keeps expanding forever?
Everything will disappear.
Everything will disappear. It'll get so far away that we'll all be isolated. Every location will just be completely isolated eventually. That's the outcome if the density is too small. The density has to be, it turns out, something like 1 part in 120 decimal places, 1 part in 10 to the 120th of the exact critical density for us to have a universe that still exists. Our universe still exists. What does that suggest to you? The fact that density has to be really precisely this value or we don't exist. Okay, to a lot of us, it means that we were created. We have arguments that are called fine-tuning arguments, talking about the different constants and values in nature and how precisely they have to be exactly where they are. Any deviation, no life. Remember I told you Fred Hoyle, he rejected the Big Bang Theory. He mocked it because he believed it required a God. And yet when he was studying the energy levels in the nucleus of a carbon atom, he said it has to have exactly this value. You can't have carbon, you can't have life, and it had exactly that value. He said, it's inconceivable. And yes, that word means what I think it means. That we can have exactly these energy levels without a designer. And so he decided later in his life that there must be a God because we have carbon. So these different outcomes are interesting. We have the isolation if the density is too low. We have the big crunch if the density is too high. There's actually another one that we now have to worry about. What if the rate of expansion is expanding? Or rate of expansion is expanding. Accelerating. You see the picture on the right. If the rate is accelerating, then what's going to happen? We're going to get isolated, right? But they call this the big rip because it would rip apart the fabric of space-time. So we have a lot of different options here. We have different graphs there, and you can see that the actual age of the universe depends quite heavily on which one we're in. What we can say for certain on this graph is that here's where we are right now. And if the density is higher than the critical density, then the age of the universe is not that old. And if it is the coasting case, then it's about 13 billion. And if it's this accelerating case, then it's more like 14 billion. So these are all things we want to know about. One thing we really like to know about then is, what is the density of the universe? We'll get to that at the very end of we'll get to how scientists come up with it at the very end of the lecture. So a first step along the way is trying to determine how fast things are moving if they're very far away. If the rate of the long-held belief was that the rate of expansion should be decelerating because, of course, density is not zero, that the rate should be decelerating, which means that if you look at things that are really far away, you're going to see them traveling at a slightly different speed, and they're actually going to fall a little below the straight line from Hubble's constant graphing because of the deceleration. They were going faster back in time. So it was discovered in the 90s that we could use type 1a supernovae. What is a type 1a supernova? Okay, it is going to occur when you have a binary. Not neutron. White dwarf. So white dwarf is part of a binary system, so it's gaining mass. It reaches the Chandrasekhar limit, and big explosion. The brightness of those, by saying the spectrum, they can analyze and know if the spectrum is like this, it's going to be this bright. And so they can use those as standard candles then to determine how, they know what the luminosity of it is. You measure the brightness and you can calculate the distance. And so these are some examples that NASA analyzed. And you know what they found? They found that those babies were not the distance away they should be according to Hubble's constant if we had constant expansion. They're above the line, indicating that the expansion of the universe is accelerating. We're going faster now than we were in the past. That's troubling. It's troubling because we have this thing we like to call the first law of thermodynamics. it says that energy cannot be created nor destroyed. But if things are expanding, the energy is going up. Remember, we had kinetic energy, energy in motion. The faster it's moving, the higher the energy. So if things are expanding, we are adding energy to the universe. And so this brings up the big, where's the energy coming from? And what is our scientific answer? That is it, but we put a name to it. Instead of shrugging our shoulders saying, we say, well, obviously it's dark energy. It's energy we know nothing about. Right? Exactly what you said. So we say that there's dark energy that's causing this acceleration. How much dark energy? We'll see some pie graphs later on. But roughly 70% of the universe is dark energy. 70% is we have no idea that's making us expand faster. So here's a picture illustrating, and we have like 4 or 5 different pictures illustrating the Big Bang in different ways for this lecture. After all, the topic is the Big Bang. Illustrating what's going on with the Big Bang. So we have, notice this number here, 13.8 billion years. That is the current best understood age for the universe. And I totally forgot to bring, I'm going to go back to my office just for a minute to bring my visual aid, unless I can't find it, then it'll be 2 minutes. Because then we can play with my visual aid during class. There it is, I see it. I know some of you believe that the answer to something, life and everything is, well, what is the answer to 42? But I'm here to tell you this is the answer to life and everything. This is the ultimate answer to all of the questions that we've been talking about in class today. And I need to blow it up. If we would just make it warmer in here, it would probably be, fine, right? You guys learned your gas laws. Blow it up. Really? Somewhere I got this for free, which is my favorite price. We will learn what this is, but for now, just don't mess with the universe. That's what we have to understand this by. So, looking at the history, we have the Big Bang. Notice what's happening to the size thereafter the Big Bang. It's expanding really rapidly. This is called the inflationary period. It's a relatively recent, like within the last 25-ish years, idea that answers 2 of our most difficult questions in astronomy. And then we have it slowing down like you'd expect. And then we have something causing it to accelerate again, that dark energy. How are we going to learn more? This was the original name, the Next Generation Space Telescope. When was the Next Generation Space Telescope supposed to launch? I looked this up before class because nobody knows this, right? 2007. Well, they finally finished the now named James Webb Space Telescope in 2016. Did you know that? It actually was fairly well publicized because after they finished construction of it, the telescope is ready to go. They're not just launching it, they have to test it. And when they were testing, they were opening up the sun screen, which I believe is that little platform there you see. It's a mylar sheet. And things malfunctioned and it ripped up. And so they delayed. At that point, I think it was supposed to be, launched in 2018. And they delayed it to 2020, and then like a month later, after a committee had reviewed everything, they're like, March 2021, we think we'll get this going. So, I mean, what's 14 years, right? It's still going to be launched. Just it takes forever with these kinds of projects, especially when you've got really deep pockets funding it. There's really not a lot of incentive to go fast and standard budget. You just want to make it the real deluxe. And it's going to be the deluxe telescope. I mean, No expense spared for the Webb Space Telescope. You understand what I'm saying, right? So this telescope will help us to answer more questions about the expansion of the universe, hopefully get some better understanding, maybe about what's going on with that dark energy. Now, we have one number so far, or one method so far, one method for dating how old the universe is. What was that method for dating how old the universe was?
Yes.
The Hubble constant. Well, here's a second method, and this one's real logical-like. If you measure the age of all of the stars, you can be assured that the universe is older than the oldest star. Seriously, guys.
Well, good thing that you guys are baseball players.
Are you with me? You can be assured that the universe is older than the oldest star, right?
Yeah.
And so, examining stars in clusters, scientists have been able to, they believe, identify more and more accurately the age of old stars. Right? You have things like, look at the HR diagram. We know that stars, when they form on the bottom of the main sequence, and then they move across the main sequence, not up or down, but across. And so by looking at these stars, we can figure out, okay, it's this mass, should have this lifetime, it's here in the HR diagram, so it's this old. We can determine ages of stars. And the oldest stars found are in the ballpark of 12 to 13 billion years old, based on an understanding of star ages. Completely different method. Get a fairly similar age. So that's a second saying, hey, this is how old we believe the universe is. This one here, I was just trying to figure out where to put it. I changed the order of these slides quite a bit from the textbook. Do you guys read the textbook? Nah. Here it does sometimes. You know, the day before a test.
Yeah. Not quite that clean.
I'm just joking. I don't know why we're joking or moving today. It doesn't make any sense, does
do
it?
the day before a test also, though. Not gonna lie.
Also, good call. Also, not only. So we've talked about the expansion of the universe, and when we first brought up the expansion of the universe, what did I say was happening? Stretching the space-time continuum. So we said things like the solar system isn't stretching. By the way, you guys did know, I say that because I remember that's one of the homework questions. You guys did notice that I posted a homework assignment for you?
No.
One last homework assignment. I don't remember what number it is, but one last run at it. Yay, right? We haven't had as many homework assignments as we should. I apologize for that. Hopefully you didn't knock me out too hard in the teacher evaluations for not having enough homework.
Obviously. Obviously did that.
Well, an argument can be made for that. Okay. So the solar system's not stretching, but the fabric of space-time that we're on is stretching. And with that, radiation is being stretched. So we have light coming from something, and because of the stretching of the space-time continuum, the wavelength is getting longer. We call this a Doppler effect, but it's not the same thing. It's not the same thing as meow, right? The meow works perfectly to explain red shifts and blue shifts. But this here is a wavelength shift because of the expansion of the universe. It takes a different calculation to get the numbers from that, obviously. But that's causing radiation to get redder and redder. So now we go back. I took out the pictures of Gamow and his crew. Funny stories. George Gamow, by the way, is the one who wrote things like Mr. Tompkins, and I think it's in Wonderland, or The Incredible World of Mr. Tompkins. It's great stuff about this guy who daydreams about crazy physics things, like if the speed of light was 50 miles an hour, what would life be like? Or if Planck's constant was like 10 instead of 10 to the minus 34, what would life be like? It's things to help you understand physics because he was a Nobel laureate physicist. But he also had a great sense of humor. Just one thing to help you understand the great sense of humor of all physicists, and George Gamow in particular. Gamow, spelled G-A-M-O-W, is kind of similar to Gamma. And he was working with Ralph Alpher. I think his name is Ralph Alpher. Anyway, Alpher was his last name. And he's like, Alpher, Gamow, that's kind of like alpha and gamma, the first and third letters of the alphabet. Well, Hans Bethe was also doing research on the same topic. And so they wrote a paper, and they just put his name in there as the middle author. I don't think Hans Bethe even helped to write it. So that they can have their famous alpha, beta, gamma paper. Okay, good guys, right? Well, when they were studying this, they said, okay, from the Big Bang, there comes a time when he's called. By the way, I have to say this is way off topic, but it actually offended me. Do you guys know that song, Where in the World?
Mm-hmm.
Have you paid attention to the lyrics? In one place it says, for God has shown us by turning stone to bread. Did God turn stone to bread? No, that was one of the temptations, and he was not going to fall to Satan's temptations. And yet the song says that. I was offended because at camp meeting, I think it was this last summer, I go to Soco camp meeting. One of the pastors quoted the lyrics of the song, including that line. Like, how do you from a pulpit quote, for God has shown us by turning stone to bread? Anyway, sorry, back to this. So there comes a time in the Big Bang, early on, you have such high energy density that it's like in the sun. Energy goes this far and it gets absorbed again, then re-emitted. But after, 300,000 years after the Big Bang or so, electrons combine with protons forming neutral hydrogen atoms. This is called the period of recombination. I don't know why there's a re in it because it's the first. But suddenly the universe goes from being opaque to transparent. And so light from that period then goes out and should continue for all time. And so right now, no matter what direction we look, we should see radiation from that time of recombination. So this was a prediction made by Gamow and his team. And you know what they didn't have? The ability to measure it. Because they knew, based on the previous slide, that you should have, with the expansion, a redshift to that radiation. Now that radiation would have been like gamma radiation. But because of the redshift, it should be really, really cold, like 2.7 kelvins or so. Kelvins is a measurement of temperature. But you learned that, you do remember learning this, that wavelength and temperature are related. Wavelength is equal to roughly, I think it was times 10 to the 6th nanometers times Kelvin over temperature. And so that temperature of the radiation corresponds to a wavelength. And they said, this should be very low temperature, very long wavelengths, and they didn't have any way to measure it. Now, I'm getting ahead of myself. We're going to come to some pictures that deal with that. But that's what this is all about. This here is looking at that microwave background radiation. And from analyzing this microwave background radiation, we get the modern day answers to most of the questions we've been talking about in class today. And you have to have this redshift idea for it to make any sense. Okay, this is pictures from the Hubble Ultra Deep Field, not just deep field, but ultra deep field. And you see it has different elements with different Z values. Do you remember what the Z was? I'm sure it says it up there, but do you remember? You remember. No. It's the redshift. And a traditional redshift, Z couldn't get bigger than 1. But with a relativistic redshift, remember we did the calculation with the redshift of 5, it can get bigger. And so a redshift of 11.9, that's something going really lickety-split past away from us. And you can calculate, what the speed is based on that redshift. And so we're able to look at these really distant objects and get some idea for, we're looking back in time really close. It says they're 3% of the age of the universe today. I left this in because I talked about Lemaitre before. Remember, Lemaitre was the person who, I pronounced it Lemaitre, maybe it's pronounced differently. He's the person who came up with Hubble's idea 2 years before Hubble. But he published it in a journal that Hubble may or may not have ever seen. It didn't get much talked about. He's also the first person then, because remember Hubble's idea was farther things away, faster they're going. He also came up with that, and if you turn it around, it points back to a definite beginning. Before that, they just thought static universe. So I put that in there so we could have it. Here is the cosmic background temperature. So the temperature of the universe background, what's flying around. 10 to the minus 43 seconds. What is 10 to the minus 43 seconds? I don't know. Right? That's an incredibly small amount of time. As one of my colleagues once said, and what does time mean? If you have this much energy density, the rate at which time travels is so different from anything that we're accustomed to that I don't know even how to interpret it. But we have temperature super hot, 10 to the 30, that's roughly 10 to the 32 kelvins. Incineration, and then some, right? And then we have, notice this is a log-log graph. So the linear relationship just means it's a power law. But then we have cooling over time. And you see, in the earliest era, what do we know? It says it there, rules unknown. We don't understand any physics that would be going on back in that time frame. In the period up to 10 to the minus 33 seconds, we have forces are unified. That's part of the inflationary model we have to come back to. Then we have radiation dominates for a huge portion of the, okay, wait, that's still less than a millionth of a second when the energy is no longer dominated by radiation. It seems like that's more than half of the history of the universe, but it's because of logarithmic scale. Then we have protons and antiprotons. So here we start to have matter. Before here, it was just radiation, all energy in the form of radiation. Remember Einstein said E equals mc squared. So instead of having m, we had energy in the form of radiation. Here we're converting that into mass. And then you go further and you can form electrons. And then you can form atoms. This is the time of recombination, the time when the universe suddenly becomes transparent and light can come out. And then after the universe becomes transparent, you have galaxies forming and stars forming. On this scale, it makes it look like, there's not much time for this. But if it was a linear scale, this here would be about here on the linear scale. Just to make sure we're clear on the scale. So here's some important steps there. Step number one that was real important is when we're able to make particles. So gamma rays can give us positrons and electrons. And we can have, before that, there was gamma rays giving us protons and antiprotons. There's lots of Nobel physics in what we're studying today. I already talked about, Gamow and his group. A Nobel Prize within the last 20 years was given for an understanding of why our universe doesn't have same amount of electrons as positrons. We have lots of electrons everywhere, very little positrons. That's a hard question to answer. If the universe was formed randomly, we would expect to have equal amounts of electrons and positrons. And so there was a Nobel Prize, like I said, within the last, actually, I say within the last 20 years, I think it was. I was here at Union College, only been here 21 years, when a Nobel Prize was given for an understanding of that, although I still don't feel that it's really solid. I've read things saying, forming atoms, protons and neutrons, forming atoms. And you see, what is that? That's basically the same ideas as we had for the proton-proton chain, occurring 3 minutes after the Big Bang, and then occurring some 300,000 years after the Big Bang. We have the recombination. We start forming neutral atoms. So here's a very famous diagram of what we see when we look back in time. If we look in further distances, we're looking back in time. The picture on the left is astronomy. The picture on the right is if you look up in the sky. If you look up in the sky, you can see the sky until you get to a cloud. So this is for a cloudy day. You can't see beyond there because the cloud is obscuring anything behind it. The same idea in the picture on the left. You look up in the sky, and you can see back only until the sky becomes cloudy. Before that recombination, you can't see anything because the radiation wasn't allowed to pass, it was just reabsorbed again. So when we're looking back in time, when we see this, we're looking back to that time of recombination when radiation was allowed to pass through the atmosphere. So Wilson and Penzias. These two gentlemen, if I understand things correctly, they're working for Bell Lab. Let me stop playing. They're working for Bell Lab, and my understanding is that they were working on trying to develop microwave communications, or things like my cell phone. Do it for me. They were looking for sources of microwave radiation or things that would cause a problem for communication and how to deal with it. And in their work, of course, they found lots of things. But one thing they found, it was the same no matter where they aimed their telescope. That is their telescope behind them. That's a microwave telescope. It's basically like a big Alpenhorn, right? It's just got this big bell, and then it comes into that little, see that door? Yeah, that's where the guts of it are. That's where the telescope part of the telescope is. So they're working in here, and they're finding a signal everywhere they look. And so they're starting to think, and they're like, well, what could it be? Maybe it's because our telescope is not at absolute zero. Of course it's not absolute zero, but we know that anything that's not at absolute zero is going to give off radiation, black body radiation. Your bodies give off black body radiation. Ice cubes give off black body radiation. They give off less because they're colder. And the wavelengths they give off are longer because they're colder. So they said, well, maybe that's what's causing it. So they cooled things down, no change. Now, if you look at that baby, it's big. What do you think is going to happen when you have this telescope out? Yeah, well, they had bats. There were bats in the telescope. And of course, what do bats leave behind that we all love? Guano. So they're like, maybe the bat guano is the problem. So they got in there and they scrubbed all the guano out. No change. And then they're like, what in the world? So we've done everything we can think of. Maybe we've got to head to the library. And they head to the library and they read on the work of Gamow. And they're like, maybe that's what it is. Now, at the same time, Dickey, I can't remember Dickey's first name, he was actually trying to get a grant to look for the microwave background radiation because obviously at this time we had microwave telescopes available, and so he wanted to get a telescope for his university, microwave telescope, so he could look for it. And so he's getting ready to write a grant proposal, and so he says, read this article from these two jokers from Bell Labs, and yeah, they've already done it. And so Dickey was rather disappointed because these guys had scooped the research he was trying to do. Dickey would be like the most famous person we're talking about now instead of these two guys. But what did they find? They found that radiation coming from the background. Now, how do you know that's what it is? Well, one thing is the temperatures. The temperature is, like I said, I think it's 2.73 kelvins. But it's not just 2.73. It's uniform down to like 0.0001 kelvins. Almost exactly the same temperature no matter where you look. This here, if you look at it, it does not look like it's all the same color. Color is temperature on this. And so then you're like, is he lying to me? You often ask yourself that, don't you? You should. I mean, I obviously will never intentionally lie to you. There are some teachers who think it's funny, because when we talk about techniques in teaching, some teachers are, I'm going to say 3 things that are untrue in class today, and you have to point them out. I'm like, how would you know? Okay, and of course that would allow me to misspeak. Yep, that was one. Anyhow, what's going on here is the colors represent changes in temperature of like 10 to the minus 4 Kelvin. So you're seeing the variation in temperature, even though it's a very, very small variation. Now, what do you suppose is causing the red stripe on this? It's the Milky Way. That's not the cosmic microwave background radiation. That's the Milky Way that's causing the red stripe. So this stuff out here, that's the cosmic microwave background radiation. That's the radiation from the Big Bang, as first observed by Wilson and Penzias.
Wait, what is that a model of? It just shapes so...
This is a model of, if you look out in the sky, the different temperatures for the microwave background radiation. And like I said, it's like microkelvin variations that are shown on this. So here's a fit to the data. That's a pretty perfect fit, right? The boxes are the actual data, and then the line is the fit to 2.73 kelvins. And you can see, okay, on the right-hand side, it may be a little off. A little off. But that's about as good a fit as you're ever going to hope to find. So there have been a lot of different explorations. This here, as you can see right here, is the Wilkinson Microwave Anisotropy Probe, or WMAP. So that's the middle one up there. You have the Kobe spacecraft and the Planck spacecraft that have all been tasked to map this microwave background radiation, give us better and better understanding of it. So that picture down below, how's that different from this? They subtracted out the Milky Way. And so you're looking at the variation in temperature in, like I said, microkelvins. What does this tell us? It tells us some really important things, and the first one we have to talk about is the geometry of the universe. Everyone here, when you were in grade school, you probably learned things like the area of a circle is pi r squared. The area of a rectangle is base times height. Area of a triangle is 1/2 base times height. That's what we call Euclidean geometry. Euclidean after Euclid. Euclidean geometry is plane geometry. When I was in high school, my geometry textbook said plane geometry. And of course, I thought that meant, just standard generic, even though it's not spelled right for standard generic. I wasn't that astute. Well, that's not the only kind of geometry that exists. It's just the only kind we want to study. And when we talk about space, space doesn't have to be flat either. It's possible to have a curved space. So an example of a curved space would be if you lived on the surface of this ball. That would be a curved space. And if you draw a circle on the ball, the area of the circle is not going to be pi r squared. Because of the curvature, the area is going to be smaller than pi r squared. So your simple geometry equations don't work if it's not flat. So there's 3 options here. Flat space. That's what we know and understand. Then there's the spherical space. We also call this a closed space. Closed because you take a trip and you always come back on yourself. There's no way out. And then we have the hyperbolic space or the open space. The The hyperbolic space, sometimes we say it's like a saddle of a horse. It's got a curvature like this in one direction, a curvature like this in the other. In that case, if you were to make a circle, the area is bigger than pi r squared. So you can determine what type of geometry you're in if you can determine the radius and determine the area for a circle with that radius. If the area is pi r squared, it's flat. If the area is bigger than pi r squared, it's hyperbolic. If the area is smaller than pi r squared, it's spherical. So astronomers have set out to do that. One way you can do that is say, okay, we are going to measure the number of, let's say, galaxies in this distance. And if you find it, if you double the distance, it doesn't do the right thing. You can say, it's not flat, it's this or that. So that's one way of doing it, to do some mapping of things we can measure. Another one comes from analyzing the fluctuations of this. The fluctuations of temperature are actually the key thing for determining virtually everything we know about the universe. So here we're looking at the fluctuations. And if you had a spherical or closed universe, your fluctuations would get, you'd have bigger fluctuations, or bigger space between the fluctuations. If you have the open or hyperbolic, you'd have smaller spacing, and flat is intermediate. This, of course, comes from theory that you have to know is beyond my understanding. And if you look at the actual information, the actual fluctuations, they fit almost exactly to the flat. And when I say almost exactly, I mean they're pretty exact. And so astronomers have determined that our universe has a flat geometry based on looking at this cosmic microwave background radiation. What does that flat geometry mean to us? Well, I got to go back like 20 slides. Okay, I only have like 20 slides, but go back about 17 slides. There. Nope. There. It means that we have exactly the critical density and are on a course to last forever without shredding. That we have exactly that critical density. That's an outcome from looking at those fluctuations. And then from this outcome, they can then further extrapolate to determine the age of the universe. And so it's from this data that we get the age of the universe is 13.82 billion years old. So looking at the wavelength of this radiation and those fluctuations tells us the age of the universe. Plus along the way we have that geometry of the universe that comes from it. Okay, there's where I was. Nope, here's where I was. Based on knowing that we are at the critical density and the measurements of the dark energy, of the dark matter. What's dark matter? What's the difference in dark energy and dark matter? Because they're both dark. To me, that gets it confused. We talked about dark matter already before today. What is dark matter?
Is it like I guess the materials, the elements that we don't know about that are out there but affect everything?
Okay, it's the mass that we know has to be out there because we can map rotation curves, but we can't find it. So dark matter is mass that we can't find. Dark energy is stuff that's causing the universe to expand. It's going to have mass associated with it as well that we can't find. And so we have here our current understanding, 68% of the universe is dark energy, 27% is dark matter, 5% is ordinary. Yay. Now for our last topic. Our last topic is going to be on inflation. When I was a child, we talked about inflation in financial terms. Here we're talking about a completely different thing. We're talking about the beginning of the Big Bang. Two huge problems. One we had in the last test, that horizon problem. Things that are so far apart from each other that there could have never been any signal transported between them, and they have reached equilibrium in temperature, as observed with this. Right? This is the key to having, we've got a problem. So that's one problem. Another one is called the flatness problem. We've just talked about geometry. It's determined that the density is right at the critical density, we're flat. Well, how do we get to have the critical density? If it wasn't exactly what it is, we couldn't be here. Those are two huge problems for cosmology. Well, Guth, I can't remember his first name either. Guth was actually studying magnetic monopoles. Theoretically, you can have a magnet that's just a north or just a south. Never known to exist. But theoretically, you could. In his calculations, he determined that, his book is kind of funny, he says that if he could make a particle accelerator that went outside of the solar system, he could generate particles with enough energy to create a magnetic monopole, but the federal government wouldn't fund it. So he did some research, and the only place where you could have enough energy anytime ever in the universe to create a magnetic monopole would be in the Big Bang. In which case, there might have been enough energy to make 7 magnetic monopoles for the entire universe. Well, along the way, he ran into these problems and came up with a very interesting solution. Early in the development of the universe, remember the forces were all combined, and then you have the forces separate out. You have 4 known forces: strong nuclear, weak nuclear, electromagnetic, and gravity. And when those forces become separate, all of a sudden a huge energy release and the universe expansion just accelerates. So his theory is you have the universe expanding here, and then you have this inflationary period with hyperinflation, like Venezuela. And during that time, the fabric of space-time is expanding faster than the speed of light. Nothing is moving faster than the speed of light. It's the fabric that's expanding. And because of that expansion, you have things that used to be close enough to communicate that they can reach equilibrium are suddenly ripped so far apart they no longer can communicate. So the horizon problem is theoretically solved because they used to be close enough they could communicate, and then space stretched on them so they no longer can. The flatness problem, if you take a balloon and you blow it up, it gets flatter and flatter. And no matter what the density is, during that inflationary period, the density is going to move toward the density required for flat. So that gives a solution for those two problems. We're out of time, I see that. Have a great Monday.